essentially a point. And we're going to define the position, the velocity, and the acceleration associated with this mass. We want to do this in one dimension. This will cover the fundamental concepts of motion in one dimension. And from that one-dimensional motion, we'll be able to make up the three-dimensional motion in our space. It turns out that motion in 2, 3, and higher dimensions is actually just like having independent motions in each of the separate dimensions. So once we understand how to do one-dimensional motion, then we can do that in each of the three directions, x, y, and z, of our three-dimensional space, and get motion in 3 dimensions. As we know, a single mass moves in 3 dimensions in our space. So if we have some kind of mass, here's our x, y, and z coordinate, and here's the mass m, and it's going to move in some path. This might be a baseball, curved ball, the way I've drawn it here, and this mass is going to move at different times. It's going to be located at different places. And we can think of that as a vector that goes to these positions. R is a vector. So we could write R as a vector that depends upon time, and that R vector would be in 3 dimensions. We're not going to do 3 dimensions yet. We're going to concentrate on just one dimension like X and master that with our definitions, and then in the next chapter we will approach kinematics in 2 and 3 dimensions. The internal behavior within that mass can be ignored. If we blow that mass up, like if it's a baseball, whatever's happening with the molecules and the atoms and the elementary particles, the nuclei, can all be ignored. That is the most wonderful thing about physics, is we can ignore the internal motions, and you can actually prove that mathematically. So what we are really dealing with is the point there that could be considered the center of mass, and that's really what we're talking about in this motion if you want to think in a very exacting way. So we can treat all of that motion as moving with the center of the mass. Now, if I just look at a particle like this baseball here, I'll make it a little bit rounder, and as that particle moves, at any given instant, it has 2 things that characterize the state of the particle. Those 2 things are the position, which would be x, and the velocity, v. And here we would say that x is in the x direction, of course, and this velocity is the velocity in the x direction, which could be positive or negative. In 3 dimensions, I would have to specify x, y, and z, and velocity in the x, the y, and the z direction, so that would constitute 6 numbers. So the state of a system, the state of an object, a particle, in 1 dimension is given by 2 numbers, the position and the velocity. And what we want to do is we want to take those 2 numbers and predict the future. In other words, we want to predict where that particle will be at a later time. In order to do that, we have to define carefully what we mean by velocity and acceleration. Now, if you know calculus, then you understand that if position changes with time, then we can define velocity as a function of time as the derivative of x with respect to time. This gives us what is called instantaneous velocity. But you don't have to use calculus here. You can get an approximate velocity by saying, just like we do when we're looking at a motion of a car, we could take velocity to be the change in position, and here we write a delta rather than a d for derivative. If you know calculus, you understand that this is an infinitesimal change in position divided by an infinitesimal change in time. But here we could take a finite change in position divided by a finite change in time, and this actually gives us an average type of velocity. For example, if we have a car and it goes 30 miles in 2 hours, then we can take the 30 miles, the change in position, divide it by the amount of time that's elapsed, and we can say, oh, our velocity is equal to 15 miles per hour, or better yet, miles per hour. And so you can see that this actually averages things out, and so it is an average. For example, during this period of time, you may speed up some of the time and slow down some of the time, But all in all, we're saying that in the 2-hour period, you have covered 30 miles. So this gives you an average. Up here, with calculus, we're looking at an exact instant, what the velocity is at each instant. And of course, we could then average that over a period of time if we wanted to take the average velocity or revert back to this. Well, this is what we mean by velocity. What do we mean by acceleration? Well, the acceleration, as you know, is how you change velocity. Simply like with a car, we call it the accelerator. We don't call the brake a deaccelerator, but we could. The accelerator accelerates the car, making the velocity increase. The brake decreases the velocity or decelerates the car. That's otherwise known as a negative acceleration. Now, how do we write that? Well, in calculus, we would write the acceleration as a function of time is the derivative of the velocity with respect to time. Likewise, that since the velocity is the derivative position, this becomes the second derivative with respect to time of the position as a function of time. So we can either think of acceleration as the first derivative of the velocity or as the second derivative of position. If you're not using calculus in your course, then you can write this very approximately as an average velocity by saying this derivative is really the velocity final minus the velocity initial. In other words, a change in velocity over a change in time, or write it this way, change in velocity over change in time. And that gives us an average acceleration. We've covered all these points and how we seek to predict the future position when we know the position at a previous time. We have now defined velocity and we've defined acceleration. And now what I want to do is give you some examples of how we would compute this with something simple. And the simplest thing that we can work on here is the following. We want to look at something like a falling mass or a mass that's thrown upward. And how would we do that? Well, we first have to define what we mean by a constant acceleration in the gravitational field. And I believe that is, we can cover that here, but it's also covered down in these problems here. So why don't we wait to the next section to go through those examples rather than do it twice. But you can see that if we have an object that's falling, then it's going to go faster and faster and faster as it falls. The acceleration will be constant, it turns out. And we're going to find that out in the next section. That although the acceleration is constant, the velocity is changing fast to be faster and faster and faster. And we'll derive those equations. Now that we have defined velocity and acceleration, we can look more explicitly at the equations that we have for a particle that's moving in one dimension. We're going to discuss problems where we have constant acceleration and also constant velocity and see what they're like. If our velocity is constant, the velocity at a later time is equal to the velocity at an original time. So you can see that the functional form v of t is equal to v of 0. In other words, when t is equal to 0. When that's true, it turns out that the position at a later time is the first position plus that velocity times the time. Well, how do we know that? Well, if we use the simple equation that we had earlier, which said that if we look at the definition of velocity, you recall that velocity was equal to the change in position in calculus over the change in time. So we can rewrite that as dx is equal to v times dt, integrate both sides using calculus, and this gives us x minus x naught, the change from one position to another position. This is actually the integral of dx is going to be x evaluated between x and x naught. So that gives us this times the integral between the velocity at time t is equal to 0 and a later time t. And so since v is equal to a constant, it moves outside of the integral and just stays as, let's call it, a constant velocity, times the integral of dt from t to 0, so it'd be t minus 0. In other words, if we move this initial position over here, we then get the important equation that x is equal to x naught plus velocity times time. Now this you actually knew as an equation probably when you were in about the 4th grade, because this basically says the distance that you travel is the velocity times the time. So if you're going 60 miles an hour and you go for a period of 5 hours, then you can see if this is miles per hour and this is hours, the hours will cancel out and you'll end up with 5 times 6 or 300 miles that you would have gone in this 5-hour period. Now that's assuming you started from a position that we might call 0. But if you were already 20 miles down the highway or at mile marker 20, then you might take that initial position and add it to how far you went. But this is how far you went in that length of time, velocity times time, and you may add it to an initial position that would be similar to a mile marker when you began marking out your time from t is equal to 0. So you'd say here, at time t is equal to 0, I was at mile marker 20, then I went 300 more miles, so I'd have this plus 20, so I'd go a total of 320 miles, go a total of 300 miles up to mile marker 320. And I assume that everybody here knows that the mile markers on the highway are marked out in miles and not in kilometers in the United States. In other places, in other countries like in Europe, those are going to be measured out in kilometers, which we should be using. Now that gives us an example of a constant velocity problem. Let's move down now and look at what happens when we have constant acceleration. Well, there we have to start with the same kind of calculus equation. And if you don't know calculus, it's okay. All you're responsible for is learning this equation here. But we're going to expand that equation a little bit. I'm going to derive the next one. I'm going to say, okay, dv dt is equal to the acceleration. And I'm going to make that a constant. Or just remember that this acceleration is a constant. That way I can multiply both sides by the time. It's a times dt. Integrate both sides, and the integral moves right through the constant. So I integrate this from v naught to v, and that will give me a v minus v naught, and that will be equal to a. I'm going to integrate from 0 to time t. That will give me a times t, or equivalently, if I move the v naught over here, the velocity at a later time t will equal to v naught plus acceleration times time. This equation is valid if a is equal to a constant. So when I have constant acceleration, then of course my velocity that I start out with is going to increase to a final value. So I might say I start out at 60 miles an hour, and I might accelerate at a rate of 2 miles per hour. And I might do that for 3 hours. If I did, then you can see that for a period of 3 hours times this acceleration, that would give me 6. And I would end up going with a final velocity of 66 miles per hour. You'll notice here that this hour here will cancel the hour right here. And the hours, for the hour squared, leave me with a mile per hour. So I just take the acceleration and multiply by the time, and then add to my original velocity. If this were deceleration, if I were slowing down, then I would use a negative sign.